Hi, welcome back to our Open Blockchain screencast series. This time I'll describe how we publish blocks to our blockchain. But first, please remember our disclaimer that this is for information only. No contracts, no liability, no obligations assumed. Presentation materials are public domain, our project is 100% open source, and we depend on some components that have their own open source licenses. First, let's review what a block is. We're going to call our blocks chunks so that we don't get confused with Ethereum blocks. In our last screencast, we described how files are encrypted and then formed into one or more chunks. Each chunk contains encrypted text and a signature. The next field lets us turn very large files into a set of chunks. Let's say that miner M is publishing a chunk. The miner has to do two things. First, it adds the chunk to IPFS, which means Interplanetary File System. IPFS is a separate open source project available under the MIT license. IPFS is like the World Wide Web, except that all the resources are known by a hash value instead of a URL. Under the hood, IPFS uses BitTorrent to make the file available in a peer-to-peer network fashion. When we add any chunk to IPFS, it calculates the hash of the chunk contents and uses that value encoded in base 58 as the chunk name. Every name starts with QM because it indicates the hash algorithm used. In this example, our chunk name ends with a B. But adding to IPFS does not automatically notify our other miners. So the second thing we have to do is inform them that this new chunk exists so that they'll know to retrieve it. The publishing miner calls a publish method on an Ethereum smart contract. It passes the public key of the receiver and the hash value of the chunk we just published. The smart contract simply places an event in its log. Every other miner is watching this same smart contract for these log events. When another miner notices the event, it gets the chunk's hash value from the log. It then does an IPFS get to obtain the chunk contents. Now, if every miner fetched every chunk that was published, then every miner would have a full copy of all of the chunks ever published. This would be great for redundancy, but somewhat wasteful of space. After all, storage costs money. We can organize our miner population so that each one stores a subset of all the chunks. Consider that every miner has one Ethereum address. Let's group our miners according to the last character in that address. All miners whose address ends in 9 belong to the 9 group, and all ending in B belong to the B group. As Ethereum addresses are in hex, there would be a total of 16 groups. In this example, we're only showing 3 groups to keep it simple, but you can imagine groups 0 through 8 above and C through F below. We assume a large enough miner population so that each group has many members. Now, when an event is published, each miner converts the base 58 encoded hash value to hex and checks the last digit. For the example, pretend that our hash decodes to something ending in a 9. So every miner whose Ethereum address ends in 9 will use IPFS to download that chunk. So when we're in steady state operation, each miner in a group will end up storing an identical set of chunks, and each miner stores 1/16 of the total overall file set. Ethereum will serialize the events and ensure that they occur in the same order on all nodes, so our miners will be able to fetch and store the chunks in the same order. In our next screencast, we will show what the miners do with these chunks and how they enforce consensus.